Hello and welcome back. This is problem H, grade 1 from Atcoder Educational DP contest. The problem states that there is a grid with H horizontal rows and W vertical columns. Let Ij denote the square at the ith row from the top and jth column from the left. For each I and j between H and W, the square Ij is described by a character A of Ij. If A of Ij is a dot, then that square is an empty square, and if it is a hash, then that square is a wall square. It is guaranteed that the squares 1 1 comma hw are empty squares, and we need to Taro will start from square 1 1 to reach hw by repeatedly moving in the direction right or down to an adjacent empty square, and we need to find the number of paths, unique paths from the square 1 1 to hw. And since the answer can be extremely large, we need to print the answer modulo 10 to 9 plus 7. Constraints are h and w up to 1000, and the grid, the starting and the ending cells are empty squares. So let's look at the problem. Okay, first of all, if we are given a grid, let's say this is a 3 by 3 grid that is given to us, and some of the cells are blocked. Let's say these two are blocked. In that case, we will arrive, let's say this one is not blocked, so this, let's say only this one is blocked. In that case, there can be two possible paths from the starting cell 1 comma 1, which is this one, to h comma w, the first path being from the top like this and the second being from the bottom like this. And now if you convert this grid into a graph, so it will be as follows. So the cell 1 comma 1 will be represented by this, next 1 comma 2 by the same 1 3 2 1 2 2 2 3 3 1 3 2 and 3 3. Next up, if we add an edge between the adjacent nodes wherever it is possible, so all these cells are empty cells, hence these edges can be added, but this edge will not be added because this is a blocked cell. So let me also mention that here. So this is a blocked cell, so this cannot be a path between any adjacent nodes. So this graph of grid will be converted into this graph by following the convention as we saw in the question. Now if we rearrange this just for clarification, then this is the starting cell 1 comma 1, and this diverges into two nodes, not diverges but has two possible ways to go from that node to other. This is 1 comma 2 and this is 2 comma 1. This would be 3 comma 1. This would be 1 comma 3, other one, and this will end up at the final node, which is h comma w. Now as you saw, this problem of counting paths in the grid is same as counting the number of ways to reach from this node starting to the ending node. Hence this is how we can represent this grid as a graph. This is the main idea. Now if you notice clearly, this is a directed graph, directed acyclic graph. And this acyclicity is important because we can apply dynamic programming whenever a graph does not have a cycle. So let's say this is a starting node and we can have only two possible ways from that node to the other one. And notice that any node which is interconnected or has intermediate paths in between them can only be connected through an edge to a non-connected node which lies below, which lies in the uppermost part of it. So these edges do not go in this direction. This edge does not go in this direction, hence this graph is acyclic, does not contain a cycle. So in short, we can formulate the graph and count the number of ways to start from a current node, from any node as per, and end at some node. This will be 1 comma 1 and h comma w in our case. And this graph has number of nodes equal to h times w, because each cell in the grid is one node in a graph. So this, let's say I comma j is a node, particular some node in the graph, which has some intermediate edges and neighboring vertices. And the number of edges can be of order. So each node can be connected to either its downward neighbor or right neighbor. So hence it will be twice hw, which is same as h times w. Now to count the number of ways to start from current node and end at some other node is same as saying that we need to count the number of unique paths between them. So say we were given a node and there were these 4 unique paths to reach node, let's say E. Now if this node has neighbors B and C, so 4 ways to reach here, 4 ways to reach at A, then it means there are also 4 ways to reach at B and 4 ways to reach at C. This is because you can traverse any of these 4 paths, take an edge and arrive at B. Traverse the first path, traverse the same edge, arrive at B. Traverse the third path, traverse to the same edge, this one, and arrive at B. So there are 4 choices or 4 unique ways to start from some, let's say this were intermediate paths, right? We only need to know what were the number of unique ways to arrive at A, and using that information we can know what are the ways to arrive at B. So ways to arrive at B is same as ways to arrive at A if there was only one edge, right? So let's take another example. Say we were given a node A and there were, let's say there were 2 nodes and we know that, let's say there are 3 ways to arrive at A and 2 ways to arrive at B. Now in this case, if we need to know what is the number of ways to arrive at C, then the first could have been that we choose one of these path 3 ways, or choose 2 of this through node B, hence 2 ways from here. Hence the ways to arrive at C would be ways to arrive at A plus ways to arrive at B. This is the main logic for counting the number of paths from one node to the other. And using this, we can update the answer from one node to the other. And for that, we need to update the answer in some particular order. So we need to know, so we cannot update the answer for let's say A, then B, but C lies to the left of A. Then we must proceed in some particular order in this manner 1, 2 and 3, so that the answers, let's say there was one way to arrive at C, then there would be one way to arrive at, say there was another node D and it had one way to arrive, then A will have two ways and B will also have two ways. And this order is important because if you evaluate these summations in different order, then it may result in a incorrect solution. So to find out the correct order, we use topological sort. It will basically give us the ordering of nodes, so that let's say the ordering is A of I, then A of I node lies to the left of A and A of jth node lies to the right of, let's say I is less than j. Then there is an edge from this node to the other one, or there is no edge, so that if the nodes are placed from left to right, the edges always flow from left to right in an increasing manner. So this was ith node and this was jth, so the edge is either present or not. And this is how topological sort is implemented, and using this we can arrange the nodes. Start from the starting cell 1, 1. There was one way to start from, there was one way to arrive at this, and let's say there were two of these edges present and this one. Then we will evaluate this is already known. Then we will evaluate its neighbors, which will be these two nodes. So one way to arrive here, one way to arrive here, and then this would be evaluated, no neighbors for this node. Then this would be evaluated, they update the answer for its neighbor, one way to arrive at this node. And this is how we will update the answer for the entire ordering of nodes. Next step, let's understand how counting ways affect whenever we are updating answer from one node to the other. Let's say there were three nodes. We know the number of ways to arrive at each of them. Let's say 6 ways to arrive at node A, 12 ways to arrive at node B, and let's say 3 ways to arrive at node C, and each of them being independent and unique. Okay, now if we want to update the answer for, let's say, node D, then all of these ways will be accounted uniquely, because we can start anywhere from this, end up anywhere here, end up at this and destination, start anywhere from this, end up here. Similar for all of these ways. Hence, the total number of ways to arrive at D would be summation of, let's say, node U, number of ways to arrive at node U, where U is a predecessor of A, predecessor of D, which means in the topological sort, the node D would have been connected to some number of nodes, right? So there would have been a edge like this, and we need to know, to update the answer for node D, we need to know the answer for A, B and C, which are, we can say, predecessors or even adjacent, reverse adjacent nodes of node D. This is how we are going to evaluate it. Now let's look at the recurrence relation. If we know the order in which we are going to evaluate the number of ways for all nodes from 1 to n. Let's say order is p1, p2, p3, and pn. So to update the answer for any node pi, let's say pi, the ways to arrive at pi must be known. If it is known, then we can update the answer for neighbors of pi by adding its number of ways. Let's say neighbor ni, n of p of I, which is a neighbor, ith neighbor, pith neighbor of this node. So ways to arrive at any neighbor of p of I would be incremented, not exactly a summation, but it would be incremented by the number of ways to arrive at p of I. So n of p of I is basically adjacency list of p of I. This is how we are going to update the answers, and the recurrence relation looks as this. And the base condition is the starting node, which was 1, 1, is a base condition saying that there is one way to arrive here, and this answers would be updated in this fashion. If we are analyzing the grid as graph, so one way to arrive here, then this would again be 1 here, then this would be 2 because this and this would be added, so 2 here, this would be 1, so here it would be 3 because this had 2 ways and this had 1 way, so 2 plus 1 equals to 3. This is how we are going to update it. Now let's look at the implementation. We take an input hw, size of the grid, and the empty or non-empty values for each cell of the grid. Then we start the recursive function saying that we need to count the number of ways from this cell, which is starting cell, equals to 1, 1 in the grid. Now there are some base conditions. So this function helps us to find out whether the grid cell that we are currently in the state of the recursion is inside the grid or not. So since our grid had size h comma w, the cell I comma j lies in the grid if and only if I belongs to 1 comma h. At the same time, j belongs to 1 comma w, or x and y as denoted in this variable naming, and this returns true if that point is inside the grid. So if we arrive at a state where it is not inside the grid, we simply return 0, saying that there is no way to say that there is a path from starting to ending where we are going outside of the grid. Also, if this cell is blocked, that also means that we are not allowed to perform this way, and we can simply return 0, saying that there is no way from here. Now there is a case where we arrive at the ending node or destination node, and this is one valid way, or we have found out one possible choice of path, and we can return 1 from here. This is for memoization part, and we will find out the number of ways starting from this I. The convention is x comma y. We can go to x comma y plus 1 or x plus 1 comma y, and the recursion will itself handle the blocked case and outside of the grid case, so we don't need to explicitly handle it before calling it for computing the number of ways individually. So this will be modded and the final answer will be written from here. The time complexity for this approach is order n square, or you can say order h times w, because there are this entire state will be memoized, and there are order h possible values for x and order doubly possible values of y, and both of them would be memoized, giving us the final time complexity where the transitions are only 2, hence it is constant time, and hence the total time complexity would be order n square. That's it about this video. If you found this useful, or if you have any doubts or suggestions, do let me know in the comments. Thank you.